We saw in the previous video that we can extend the basic idea of angle from ordinary 2D geometry, Euclidean geometry, to one which measures the amount of rotation of a line fixed at one point and rotating about that point. So, and there we say that the basic trigonometric functions, which we probably already know, they also can be extended to those angles, that is negative angles and angles which exceed 180 degree, 360 degree in fact. So here we will see that extension, and this part starts like this. You are probably familiar with the definition of trigonometric functions of an acute angle. For example, this angle, this is an acute angle, it is less than 90 degree. Now this is the right angled triangle definition that almost all of us are familiar with. What we do, we draw a right angled triangle, one of whose angle is that acute angle, say theta. Now the side of the triangle adjacent to that angle, which is different from the hypotenuse, is called the adjacent side, and the side which lies opposite to that angle is called the opposite side. In another terminology, this side is called perpendicular and this is called base. Here, however, we will call them opposite and adjacent. Now we know that these basic 6 trigonometric functions have these definitions. Sine theta is opposite divided by hypotenuse, and its reciprocal cosecant theta, cosec theta, is just the reciprocal, hypotenuse divided by opposite. Like that, cos theta, cosine of theta, is adjacent divided by hypotenuse, and its reciprocal is secant theta, it is hypotenuse divided by the adjacent side, side length. And then tan theta is opposite divided by adjacent, and its reciprocal cotangent, cot theta, is adjacent by opposite. Now we are going to extend this to negative angles and angles which are not acute, obtuse angles, in fact angles exceeding 360 degree. So we extend this definition to obtuse and negative angles in what way? By first placing our angle in the standard position. We have seen in the previous video what the standard position of an angle is. That is, you have to place the angle in such a way that the initial, the fixed line, fixed ray of the angle matches with the positive direction of the x-axis, and the vertex of the angle coincides with the origin of your coordinate system. Once you do that, the angle is said to be in standard position. But not just that, in a circle of radius r. Okay, standard position in a circle of radius r, and we will see, we will draw the figure where we will see that the angle of course is in standard position, and this circle of radius r has its center at the origin. We then define the trigonometric functions in terms of coordinates of the point P, x comma y, where we will now say what P is. So let us first complete writing this, and then we will see what we mean by this. Where the angle's terminal ray intersects the circle. P is the point where the intersects the circle. So let us first draw the figure and then only we can properly define this extension. Now in this drawing, since we need to draw a circle, you can imagine that I will draw a very crude circle. My freehand drawing is very bad, but it will be enough for our purposes. So this is the positive direction of the x-axis, this is the positive direction of the y-axis, this is our origin. So thus in the name of a circle of radius r, say I have drawn this. You can already see that I have not been able to match it properly, but that's just it. Okay, so now what we are saying is that we extend this definition to obtuse and negative angles by first placing our angle in standard position. Okay, now because we are talking about an extension, so let us actually take an obtuse angle and put it in standard position in this way. So in standard, okay, what is the angle? The angle is this angle, theta, radians. Okay. So the angle is this. Now it is in standard position because its fixed ray or initial ray matches with the positive x-axis and the vertex of the angle lies at the origin. So this is our obtuse angle, and what we are saying is that we then define the trigonometric functions in terms of coordinates of the point P where the angle's terminal ray intersects the circle. This is the terminal ray. This is the terminal ray because it has gone through this rotation and it has finally settled in this position, in this terminal final position. Now this terminal ray intersects this circle at the point P, at some point P whose Cartesian coordinates are x, y. Okay, it already looks somewhat messy. Let me just rectify it a little bit. So this is the point P. Now we are going to define these trigonometric function values of the angle theta in terms of the coordinates of P. Okay, and for a moment let us just keep these old definitions. Let's not clean that part. In what way? In this way. Now we are going to present here another such array. Sine is defined like this. Sine theta is, do not confuse between this theta and that theta. Okay, this theta is that acute angle theta which comes from that previous diagram in that triangle, and this theta is now this one, the obtuse angle theta. Oh, and I forgot to show that the radius of this circle is r. So this much is r. Now sine theta is defined to be equal to the y coordinate of this point divided by the radius r. cosecant. I don't have space for writing them consistently like this, but anyway, let me write it just below this. CSC theta. Some people also write like this, cosec theta. In this text, however, the authors use CSC. I think this is old usage. It is just the reciprocal of sine, just like the old cosec is the reciprocal of the old sine. So this new cosec is the reciprocal of the new sine. Then cosine. Cos theta is defined to be the x coordinate divided by the radius of the circle r, and its reciprocal secant is defined to be r divided by x. Then the tangent function tan theta is defined to be the y coordinate divided by the x coordinate. So y divided by x, and its reciprocal cotangent is cot theta equal to x divided by y. So you can see that no matter what the final position of this angle, what the position of the terminal ray be, no matter wherever it lies on this circle, and correspondingly wherever the point P lies on this circle, it will have some x coordinate and some y coordinate. So from those coordinates you can calculate the these function values, and that's what these functions mean. They have now been defined entirely in terms of coordinates of some point in the plane. Okay, now a natural question arises: why are we calling these things also sine theta, cos theta, etc.? What is their for example, what is the relationship between this function sine theta and this function sine theta? Why do they have the same name? That is because these are actually extensions of the old functions, in the sense that if your angle theta is an acute angle, is actually an acute angle, then your new sine theta value and old sine theta value will be the same. They will coincide. These functions will reduce to the old functions when theta is acute. And don't make the mistake of thinking that we are defining this thing only for an obtuse angle theta simply because we have drawn the figure like that. No, our theta can be obtuse, can be acute, or can even be negative, or can be anything. The only thing is that whatever our theta is, we will put the angle in the standard position like this. If it is acute, we will put it like this. If it is obtuse, we will put it like this. The vertex of the thing is that the vertex of the angle should coincide with the origin, and the fixed ray or the initial ray of the angle should coincide with the positive x-axis. Then we will see where the terminal ray lies, and then once you decide where the terminal ray lies, you will then see where the terminal ray intersects this circle, and you will then get the x and y coordinates of that point of intersection, and you can calculate this function values. That's just it. Okay, so here theta can be anything: acute, obtuse, even a right angle 90 degree, or pi by 2, pi divided by 2 radians. So this definition is a special case of this more general definition, and in that sense this is an extension. But now we have to see that it is actually an extension, that when theta becomes acute we really have the same thing. So let's just see that. So that's what the authors say next. These extended definitions agree with the right triangle definition when the angle is acute. With the right triangle definition when the angle is acute. I am cramping this whole thing here because I need all these things, because we already have this figure. So let's just modify this and draw the next figure where we have an acute angle. So that means the circle is just like before, a circle of radius r. Some positive real number r is the radius of the circle, and now our angle is this, it's like this. So this is the terminal ray of the angle. Because it's a ray, so we are putting an arrowhead here in order to indicate the fact that it goes on like, there is no end to it. It extends like this without any bound, just like that, and that's why we put these arrowheads here on x-axis and y-axis also, just to represent the fact that they extend without any bound. We don't usually put arrowheads here, but ideally we should put arrowheads here also. We don't put because most of the times we are really concerned about what is going on in the first quadrant, but actually you should put arrowhead. The thing is that these are just bounded portions of your coordinate system that you can show. You can of course not continue drawing this without any bound. Okay, that is the idea. So now this is our angle theta, which is an acute angle. Again, the terminal ray intersects the circle at some point which has coordinates x and y. Fine. So now what we do, we draw a perpendicular from the point P on the x-axis. Then we know that this much is x and this much is y by the definition of this Cartesian coordinates. So you can now see that you in fact have a right triangle where this is your right angle, one of whose angle is your theta. So that means this side with respect to this theta, this side becomes your opposite side of this triangle, and this side becomes adjacent, and this of course is your hypotenuse. Let us now try to see if we get the same thing. Let's first look at sine theta. Sine theta is, by the new definition, y divided by r. Now because the radius of this circle is just like before r, so hypotenuse length is r, opposite length is y, and adjacent length is x. And note that because of the way we have taken and put the angle in the standard position here, so and because of the fact that the angle is acute angle, P will lie in between these 2 points. So x and y are both positive, they are actually lengths, none of them is negative or 0. So that is why x is equal to, the x coordinate is equal to the length of the adjacent side, the y coordinate is equal to the length of the opposite side, and r is of course equal to the hypotenuse. So opposite divided by hypotenuse, that is sine theta. Cos theta is adjacent divided by hypotenuse, x divided by r, and tan theta is opposite divided by adjacent, y divided by x. So yes, these functions in the first column are actually extensions of the original one, because they match when theta is acute, and because they match, the reciprocals will also automatically match the corresponding reciprocals. So these extended definitions agree with the right angled definition when the angle is acute. So that means we have understood this part. Next, let us just clean, let's put these things for now, I mean keep these things for now. I should not have actually cleaned the, I should not have wrapped up this figure. I need the figure, but anyway we will just draw the figure. This we don't need, this is the old definition. So this was, let me just quickly draw a small figure here. We will now try to see the possible values of theta that will actually give you values for these definitions. Why I am saying that? It is because these are quotients, right? Quotients of quantities. Now if the denominator becomes 0 ever, then in that case the function is undefined, because we do not usually divide by 0. In some parts of mathematics we do divide by 0, but not here, not now. Okay, so those values of theta have to be avoided. They do not belong to the domain of that function, which becomes undefined in those cases. So for that we are again drawing our original figure. Theta, so this is our P x comma y, the figure that we have in the original definition. Now looking at these definitions, you can see one thing, that sine theta and cos theta suffer no problem, in the sense that the denominators are both equal to r, which is the radius of the circle, and the radius is not 0, r is our choice. X and y keep changing depending on what the angle is, but the r is fixed. We have chosen this circle, so once you choose the non-zero positive radius, so that is fixed. So this denominators never become 0. So there is no problem with sine theta and cos theta, but there is a problem with tan theta, and there are problems like that with the other three on this column. So the authors say, as you can see, tan theta and secant theta are not defined. As you can see, tan theta and secant theta are not defined when their denominators equal 0. That is, here in tan theta the denominator is x, in secant theta also the denominator is x. Now, what is the relationship between theta and x being 0? X is the x coordinate of this point where this terminal ray intersects the circle. So this x coordinate will become 0 when? It will become 0 when it lies on the y-axis. That is, there are exactly two cases where this point lies on the y-axis. This one here and here. So if your terminal ray is this or this, then you cannot define, for the corresponding theta, you cannot define tan theta and secant theta. Now, what type of thetas will give you these two positions? You can see that if your angle is 90 degrees, that is pi by 2, pi divided by 2 radians, then you have a problem, because then your point is here, which has coordinate 0, r. Okay. But if that is not the case, and you can in fact, your angle is larger than that, then you exceed pi by 2 radians, but then 1 times pi by 2, 2 times pi by 2, 3 times pi by 2, you come here, then again you have a problem. Here also x is 0. The coordinates are, let me just write them. Here the coordinates are 0, r, and here the coordinates are 0, minus r. Don't forget that the circle has radius r. So that means pi by 2 is a problem, 3 pi by 2 is also a problem, but then this is 3 pi by 2, another pi by 2, 4 pi by 2, 5 pi by 2, 5 pi by 2 is also a problem, 6 pi by 2, 7 pi by 2. So you can see that odd multiples of pi divided by 2 radians, if your theta is that type of angle, then you have problem defining tan theta and secant theta. And the same can be said also for negative angles. If your angle is minus pi divided by 2, then you get this position. Minus pi by 2, minus pi by 2, minus pi by 2, minus 3 pi by 2, then also you have problem. Minus 4 pi by 2, minus 5 pi by 2, then you have problem. So that's why this means they are not defined for these odd multiples of pi divided by 2. Let me write 2 more, 5 pi by 2, just to show the fact that we are considering odd multiples. Okay, so for these values of theta, tan theta and secant theta are not defined. Similarly, cot theta and cosecant theta are not defined when cot and cotangent and cosecant give us problem when y is 0, when the y coordinate is 0 and the y coordinate of any point is 0 on the x axis. So the two positions where this can happen on the circle are this and this. Now what type of angles correspond to these positions? 0 radian of course is one problematic angle. Then pi by 2 plus pi by 2, that means pi radian is also a problem. Another pi by 2, another pi by 2, that means another pi. So 2 pi radians is again a problem. Then you get another pi, so 3 pi radians. So all multiples of pi, okay, they give us problem. And if you follow the clockwise sense of rotation, then also you get the similar angles, they are negative versions. 0 is a problem, minus pi is a problem, minus 2 pi is a problem. So when y is equal to 0 and hence these functions are not defined for theta equal to 0 plus or minus pi plus or minus 2 pi, 3 pi, etc. To see what is the relationship between these problematic value and these problematic values, you can see that these are all even multiples of pi divided by 2, whereas these are all odd multiples of pi divided by 2. We are not writing pi divided by 2. Had we decided to write, then we would have written 2 pi divided by 2, 4 pi divided by 2, 6 pi divided by 2, so all even multiples of pi divided by 2, or which ultimately turns out to be just all multiples of pi. Okay. So it's not that these functions are defined for all values of theta. Some of them require us to chuck out some values of theta from their domain. Okay. Note, however, I have already said, and you keep this in mind always, that sine theta and cos theta are devoid of problems. They are defined for any real number theta. Any real number theta means any real value theta radian. Okay, so these are the domains, or in other words, these are the values that we should avoid while defining these other functions. Okay, now from the way we have defined these things, we will get some immediate relationships among these functions, things that we already have seen in the old definition also. For example, tan theta is equal to sine theta divided by cos theta, things like that. So that is the next thing. Notice also the following relations whenever the quotients are defined. I need ink. Tan theta is sine theta divided by cos theta. Cot theta is up. I need more space. Then secant theta is the reciprocal of cos theta and cosecant theta is the reciprocal of sine theta. We say that whenever the quotients are defined, because these denominators can also become 0 if we don't restrict theta properly, then there is a chance that these denominators will become 0. For example, cos theta will become 0 when x is 0. Now if you recall, x is 0 when theta is an odd multiple of pi divided by 2. So for those values you cannot use this formula, and in fact for those values tan theta itself is not defined. So you have to avoid those values of theta when you are talking about this relation. Similar things can be said for these other relations also, and these are things with which we are already familiar in the old definition, right triangle definition. Okay, now the way we have defined these extended trigonometric functions, it allows us to, in fact, what can I say? It allows us to express the coordinates of a point in the plane in terms of these trigonometric functions. So now we can, you see, we have defined the trigonometric functions in terms of coordinates of a point in the plane. Now we can go in the other direction also. Suppose somehow one knows the values of these trigonometric functions for some particular angle. Then in terms of these values we can express the coordinates. Okay, so that is the next thing. The coordinates of any point in the plane can now be expressed in terms of the point's distance, precisely in terms of these quantities. Can now be expressed in terms of the point's distance from the origin which is of course r. R is the distance of the point from the origin. You can imagine, because the point in our definition of this extended trigonometric functions is actually the point of intersection of that terminal ray of our angle with that circle. So that is the point. So the radius is r. R is the radius of the circle, so it becomes the distance of the point from the origin. So now in terms of this distance and in terms of this angle theta, which they are saying what for theta, and the angle, the ray OP, okay, makes with the yes, origin and the angle the ray OP makes with the positive x-axis. So we again draw a figure for this one. So now the situation is this: you have your coordinate system so this is your positive direction of x-axis, this is your positive direction of y-axis, this is the origin, and these are the axes mutually perpendicular. So this is say your point. Okay, this is some point P x comma y. I should write it somewhat a little far away from this. So what we now do, in order to express x and y in terms of what? In terms of the distance of P from the origin. Say that distance is r, and in terms of the angle that this ray OP, we are treating OP as a ray actually, the angle it makes with the positive direction of the x-axis. So that means if we, but in what way? If we draw a circle with radius r and having center at the origin, then using our definition of the trigonometric functions, we now know what sine theta and cos theta are. Sine theta is y divided by r and cos theta is x divided by r. So we can express x and y in terms of r and theta. That's what we are saying. So since they are writing cos first, okay, x divided by r equal to cosine of theta and y divided by r is sine of theta, we have x equal to r cos theta and y equal to r sine theta. We have expressed the coordinates x and y of this point in terms of the distance of the point from the origin, that is r, and in terms of the angle that this ray OP makes with the positive x-axis, that is theta. And in this representation, x is r cos theta and y is r sin theta. So the coordinates here look like this: r cos theta, comma r sin theta. There is a difference between an equation that is appearing in a definition and an equation that is appearing in a theorem. You see, what I am trying to say here is this. You see, for example, you look at this equation and you look at this equation. Say cos theta equal to x divided by r, and let's just look at another equation, sine theta equal to y divided by r. These equations are definitions. They define these symbols, sine theta and cos theta. Sine theta means y divided by r, that is the meaning of sine theta. Cos theta means x divided by r. It's like giving people names. Okay, for example, I have given myself the name Lucifer. So Lucifer is defined to be my name. That's what it means. Okay, it does not have any other meaning. It may have some other meaning, but I'm just simply saying for the sake of understanding that Lucifer means is my name. That is its definition. Just like that, sine theta is a name given to this quantity y divided by r. That is its meaning. It does not have any other meaning independent of this. However, this equation is not coming from some definition. It is coming from some definition, but as a consequence of some definition, as a consequence of this definition. For example, our original definition of trigonometric functions. With these meanings of sine theta and cos theta and tan theta, in fact we need that also. This is also definition. We have this relation. So these are definitions and this is a theorem, this is a result. Okay. So once you have a definition in mathematics, there is nothing else to be said about the definition. I mean, you should not ask, yes, of course you can ask why the definition looks like, why is the definition like this? You can ask that question, but once you formally present a definition, then that just says that whatever symbols are being defined, they have just these meanings. Now, once you agree upon the definition, then you can ask, okay, then tell me, how am I getting, how is this equation true? Then you can prove that equation with these meanings. For example, you can actually calculate sine theta divided by cos theta using these meanings of sine theta and cos theta. You will see that you get y divided by x, which according to your definition again is tan theta, which is just another name given to this quantity. That is why you are getting this. In order to distinguish between definitions, that is equations which define something, and equations which are results, some people, you will see these things when you go to higher mathematics, put a symbol like this, a colon before the equality symbol. What this indicates is that the symbol that is lying to the side of the colon, that is the name, or that is the symbol which is being defined, and its meaning lies on the other side. If this appears on this side, sometimes we write like this also. It helps us understand what is the that is what is going on here. Sine theta is a quantity whose meaning is this, and there is nothing else to ask about this, because that's what it means. But if you see something like this and you don't know what sine theta is, then you can ask, well, what is sine theta? It may have some other definition. Okay, so that is just something I wanted to say here about these things. So what have we done here? We have extended the basic trigonometric functions, that is, their right triangle definitions have been extended to now cover all possible values of theta, not just acute angle thetas. And the good thing about this extension is that those original relations, that is things like this, still continue to be true. Even if your theta is, for example, 1000 radians or some such very big angle, which of course does not have any meaning in ordinary Euclidean geometry in terms of right angle triangle. There also tan theta is sin theta divided by cos theta, which however is not very surprising because our definitions almost immediately show that this is the case. But the other relations with which you are familiar, for example sin square theta plus cos square theta equal to 1, they also turn out to be true. Okay, so we will go to those things, but let us now see values of trigonometric functions. We now have the extended definition, so we should be able to actually calculate the values of these functions in some specific cases at least. So let's just see that. Now before we go to that, let me just quickly say something else also. From classical mechanics, you are well familiar with this somewhat crude version of the second law of Newton. Force equals mass times acceleration. Now this of course is true when the mass is not changing. So let's just assume that the mass does not change. So then your actual second law reduces to this: force equal to mass times acceleration. Now is this a result or a definition of force? It is not a definition of force. This is not what force means. If this is just, had this simply been a definition of force, then the second law is merely a definition. You are just calling the entity mass, I mean calling the quantity mass times acceleration something else. You are calling it force. So what is the big deal? You can name it something else also. That is not the law. The law says that when an object I'm saying all these things in a very crude manner. Okay, there may be physical inconsistencies in what I am saying. Just for the sake of understanding, you have an object of mass m which is not extremely large or extremely small. It is of a manageable size, and the mass is also not very great, and it is some force is acting on it, and the mass does not change. There is no appreciable change in the mass, and it gains some acceleration a. Then force equals mass times acceleration is a law, is a result like this, because this is not all about the force. You have to say separately what the force is, and for gravitational force you have a separate formula, something like this. For electromagnetic force you have another such formula. For strong nuclear force you have another such formula. For weak nuclear force, or for frictional force. So those are the definitions of the force, the type of force that is acting on your object. So this is a law, means this is a result. Okay, this is not the definition of force. In that sense I am saying all these things. So unless you say what your force is, you cannot use this equation in a meaningful manner. Okay, so let us now come to the question of actually finding out the value. And for this one also we need a figure. So let's just draw the figure first of all. So this is our coordinate system, and now we will not draw just any circle, that is circle of any radius, but a circle of unit radius, radius 1. And we again have our point P x comma y. Now if you express the coordinates like before in terms of the distance of P from the origin and in terms of the angle that ray makes with the positive x-axis like before, then this will become cos theta comma sine theta. In the general case you have r cos theta comma r sine theta. But because we are considering a unit circle, so r for us now is 1. So that's why cos theta comma sine theta. And let us now complete our figure by joining the origin and this, and also drawing a perpendicular from the point P on the x-axis. So this is our unit circle. Its radius is 1, so that means this distance is 1, and the perpendicular we have dropped from this point on the x-axis, its length is actually y, but let us write absolute value of y, because we are considering length. In this case y in fact is positive, so mod y is y, but this length is, you have to use the absolute value here, because in this particular diagram x is negative, y is positive. So if you want to say that This has length x, that will be wrong. It will have length minus x actually. So in general we use absolute value. Okay, so now what are we saying? If the circle in the definition of the trigonometric functions has radius 1, in the definition of the trigonometric functions as radius 1, that is if we are considering a unit circle, in other words. The more it rains, the more humid everything becomes, and everything becomes kind of messy. The equations defining sine theta and cos theta become this. Yes. Cos theta equal to x and sine theta equal to y. Originally cos theta is x divided by r and sine theta is y divided by r, but now r is 1. So that is why these equations look like this. We can then calculate the values of cosine and sine directly from the coordinates of P. We can then calculate the values of directly from the coordinates of P. Oh, this is theta. Without theta, how am I getting these things? If we happen to know the coordinates, know them means know the coordinates. If we are given theta, we draw the two rays giving us theta, and that is we put the angle in the standard position like this. We then locate the point P where the terminal ray intersects the unit circle, and then we read off the coordinates x and y of P, the x coordinate and y coordinate. Because we have taken a unit circle, we don't have to bother about the radius. It is 1 and it does not make an appearance here. So our x coordinate becomes cos theta and y coordinate becomes sine theta. So that way we will know cos theta and sin theta only if we happen to know these coordinates. That is, we somehow maybe the situation is like this, that this point is in a position which allows us to readily say what x and y are by some means. Then we automatically know what sin theta and cos theta and sin theta are. If not, then we have to measure these coordinates. Now in measuring these coordinates, there this triangle comes into play, and that is the next thing, or indirectly from the acute reference triangle, that is this reference triangle. Indirectly from the acute reference triangle made by dropping a perpendicular from P to the x-axis, this thing. And note that although it seems like we have been writing down this entire discussion just for this particular figure, but the discussion is generally, if your terminal ray is not here, it is say here, then also this discussion is applicable. In that case, your point P will lie here, and the perpendicular you will draw from that point to the x-axis will be this. So you can draw perpendiculars. Only in one case it will not, if your point lies here or here, then it will not mean much to draw perpendicular from the point to the x-axis. You can imagine a perpendicular of 0 length, okay, which is that point itself. But in general, this discussion works. We read the magnitudes of x and y from the triangle sides. The magnitudes of x and y from the triangle's sides, and the signs, of course, signs of x and y are given by the quadrant where this terminal ray lies, and hence where the point P lies. The signs of x and y are determined by the quadrant in which the triangle lies, okay. So what this part is saying is that, okay, so you have located the point P. Now you need to know what x and y are, because that will tell you what cos theta and sin theta are. So how do you know? There is no other way of knowing than to actually measure x and y. So what will you do? First you draw the triangle by dropping a perpendicular from P to the x-axis. Now you have this acute reference triangle. Then what you do, you using a ruler you measure these lengths. So the lengths are the magnitudes of x and y. But we cannot of course simply put the magnitudes here, we need the signs. The signs will be determined by the quadrant in which the reference triangle lies. Here in this particular figure, for example, the reference triangle is lying in the second quadrant, and in the second quadrant x is negative and y is positive. So the magnitudes you have measured, you put the magnitudes here, and with the x coordinate you put a minus sign. So that will be your cos theta value, and sin theta value will just be your y measurement, that is this perpendicular length, because y is positive. Had your point been here, both x and y would have been negative. So after measuring the lengths of the relevant sides of that reference triangle, acute reference triangle, you would have to put a minus sign in front of both the measurements to get that cos theta and that sin theta. So now we are going to look at two examples where we will actually see how to calculate these values in two specific cases. So this is example 3. Example 2 we have already seen in the previous trigonometric video. Find the sine and cosine of 2 pi divided by 3 radians. Find the sine and cosine of 2 pi by 3 radians. Now the authors have carefully chosen 2 pi by 3 because it's an obtuse angle. So all these examples are in the form of exercises. So there will be a solution and steps have been given. So in Thomas and Finney's words, this is we already know what is to be done, but again they are writing, draw the angle in standard position. And write in standard position in the unit circle. Okay, that thing has to be mentioned. and write in the lengths of the sides of the reference triangle. So our figure will roughly look like this. If you want to actually do the calculation, you have to draw the angle precisely. That thing is there. Here, however, just to illustrate the method, we are going to make a crude drawing. That is, geometrically precisely you have to draw the circle. You have to know how to draw the angle of exactly that amount, and then only you can hope to calculate the cos theta and sin theta value for that theta. So 2 pi divided by 3 radians is an obtuse angle. Pi by 3, pi by 3, pi by 3. Pi by 3 radians corresponds to 60 degrees. So that means 2 pi by 3 will be 120 degrees, and that is greater than 90. So that's why it is obtuse. So without thinking too much about 120 degree, I am just simply in general drawing a line like this. So say this is my 2 pi by 3 radians. So this is P x comma y, and we have to draw the reference triangle. So the reference triangle will look like this. Now it will be seen either from direct measurement or simple Euclidean geometry that the side lengths are like this. I don't think it will be very difficult to determine what these side lengths are from your ordinary trigonometric function. That is the original trigonometric functions that is the acute triangle definition of the trigonometric functions. From that and from those values you can calculate, because you already have them, right? And you already know, for example, what sine pi divided by 3 is. Sine 60 degrees is square root of 3 divided by 2. And you also know what this value is. This is 1 over 2. So if this is your 120 degree, this angle will be how much? The total angle is 180. So this will be pi by 3. Now if you apply your right triangle definition of the trigonometric functions to this triangle with respect to this angle, then what will be your, that means what I am trying to say here, or what I am trying to ask here is, what is the length of this perpendicular? say the length of the perpendicular is y, then you know that perpendicular or opposite divided by hypotenuse in your old definition is sine theta. But your hypotenuse length is 1 because you are considering a unit circle, so you put 1 here in the denominator, and this value you already know from your elementary trigonometric studies. This is root 3 divided by 2, and that's why this is root 3 divided by 2. Similarly, if your base length or adjacent side length is x, then x divided by hypotenuse is cos pi by 3, so that is 1 over 2. So that's how you get this side lengths. Okay, so we have now seen exactly how to find the side lengths. So now what? That means we now know absolute value of x and we know absolute value of y. So what will the coordinates of this point be? Now not only do we need these absolute values, but we need to put the signs also properly. With the x coordinate, because we are on the negative side of the x-axis, we have to put a minus sign. But with the y coordinate, we don't need to put a minus sign because we are on the positive side of the y-axis. So our coordinate values are these: minus 1 over 2 and root 3 over 2. So this is the x coordinate and this is the y coordinate, and that is why this is cos 2 pi divided by 3 and this one is sine 2 pi divided by 3. So let me continue from here. Then we have in fact calculated the thing, but in step 1 we just have to find the side lengths. And then in step 2 find the coordinates of the point P where the angle's terminal ray cuts the unit circle. That's the unit circle, or because the circle is already unit, just simply the circle. So in doing so, we get the value of cos 2 pi by 3, which is the x coordinate of P, and that is minus 1 over 2, and the y coordinate of P, which is root 3 divided by 2. So that's how you calculate cos 2 pi by 3 and sin 2 pi by 3. And note that once you have these two values, you automatically have the other values. How? I mean for the other trigonometric functions. Tan 2 pi by 3 will be sin divided by cos So you will have to use those relations, okay, which come out as immediate consequences of the extended definitions. Cosecant 2 pi by 3 is 1 over sine 2 pi by 3. Secant 2 pi by 3 is 1 over cos 2 pi by 3. And once you have the tan 2 pi by 3 value, you take its reciprocal, you get cot 2 pi by 3. So these are the values that you need to know. Once you know them, you know the others. So that's how you calculate the trigonometric function values for obtuse angle, for example 2 pi by 3 radian. Now before we go to the next example, let me just mention one thing. Why a unit circle? Do you see why? Actually, there is no need to consider a unit circle. You can, in fact, in order to calculate the value, take a circle of any radius, whose radius may be greater than 1 or less than 1 also, because in the original definition, the circle radius is r, which is any positive real number. 1, however, has been taken because it simplifies the calculation. If you take 1, the 1 just vanishes. The 1 is here multiplied with this cos and sine, right? R cos theta, R sin theta. It just vanishes and it makes things simple. That's why. Okay, now let us take example 4. Let us just observe one more thing. We have the issue of signs. Sometimes we have to put minus sign, sometimes we don't have to put minus sign. So in order to save time, you can formulate a rule to remember these signs, and that rule is this: CAST or cast rule. A useful rule for remembering when the basic trigonometric functions are positive and negative. These type of rules are okay if you are writing an exam, but I really dislike ad hoc rules like this for the purpose of memorizing things. CAST means C, cos positive, A, all positive, S, sine positive, and T, tan positive. So if your terminal ray is here in the first quadrant, then all the trigonometric functions are positive. That is because your reference triangle will be like this. So x is positive, that means your adjacent side length is positive and the opposite side length is also positive. If your reference triangle is like this, then your adjacent length is negative, but the opposite length is positive. So opposite divided by hypotenuse is, we should not say like that. The y coordinate divided by the distance of the point from the origin is your sine theta. So y is positive, your r is of course always positive, so your sine is positive. Here your both, what is tan by the way? Tan, according to our extended definition, is y coordinate divided by x coordinate. Y coordinate is negative, x coordinate is also negative. So negative divided by negative gives you positive. So tan is positive here. And here cos is positive because x divided by r is positive. In this text we are calling it CAST, cast rule. Some people also remember it as ASTC rule. Let's start here. You don't have to memorize this in order to figure out when which one will be positive. You see, it's very easy. This of course is there, but you can in fact just simply imagine like this. You are well aware with the sign patterns of the coordinates of a point in the plane from your ordinary analytic geometry or coordinate geometry. Here, if your point P lies here, then both x and y are positive. So because all your trigonometric functions are being defined in terms of x, y and this distance r, so all of them are positive. Here your x is negative, y is positive. So then looking at the definitions of the trigonometric functions, you can decide which one is positive, which one is negative, so just like that. Here both x and y are negative. Here x is positive but y is negative. So the sign pattern is this: minus plus, minus minus and plus minus. Okay, so that way you can remember, I think, much more easily. You in fact don't have to remember anything. You just look where your angle is ultimately, in which quadrant it is lying. So you look at the sign pattern that the coordinates will have, and accordingly you can just simply from the definitions of the trigonometric functions decide which one will have a positive value, which one will have a negative value. That's just it. And you have already seen in our this example 3 that once you calculate sine theta and cos theta values, you automatically know the other function values at that theta. You don't in fact have to remember the other thetas, the other function values at those theta. So next, example 4. So we have calculated sine theta and cos theta for an obtuse value of theta. Now let us take a negative value of theta. Find the sine and cosine of minus pi by 4 radians. So here also there is step 1 and step 2 where the authors are again writing those things, those same things, which I am not going to do. So instead, let us just simply draw the figure and see what the reference triangle side lengths are. This is just your solution. There is step 1. We know what we are doing in step 1. In step 1, we are drawing the, first of all, we have the coordinate axis, of course. This is our x-axis, this is our y-axis, and we draw the unit circle. And then we draw the angle in its standard position. So this is the terminal ray. Because our angle is negative, the rotation involved is in the clockwise sense. And so it is not like this, it is like this, minus pi by 4 radians. And this is our point P, whose coordinates we have to find, and we need to draw the reference triangle. So let's just first drop this perpendicular. We cannot really say drop the perpendicular because it's going up. Anyway, so this is our reference triangle. Okay. Now, how to calculate the lengths of these sides? You know that because this is pi by 4, so this is an isosceles right angled triangle where this is also pi by 4. So that means because these two angles are the same, so these sides, from elementary geometric properties of triangles, these two sides also have the same length. So these two sides have the same length, and this side has length 1. So if, for example, this side has length x, then this one will also have x. So from Pythagoras theorem, x square plus x square is equal to hypotenuse square. So that means 2x square is 1. So x square is 1 over 2. So x is, because x is a length, we are talking about length. We will come to the question of signs afterwards. So we are taking the positive square root, 1 over root 2. So this length is 1 over root 2, which can of course be written as root 2 divided by 2. This is the same thing as this. So this length is also root 2 divided by 2. Length is root 2 divided by 2. Okay. Now P, I don't have enough space for this. Do I have? I think I have. This part you have understood. So let me just simply, it's an application of the Pythagoras theorem to this reference right triangle. So let me just rub this part off. And now in this situation, in this position, x is, this is in the fourth quadrant. In the fourth quadrant, x is positive, y is negative. So that means square root of 2 divided by 2 minus square root of 2 divided by 2. And the x coordinate is your cos minus pi by 4, and y coordinate is your sine minus pi by 4. So that means if for once we write the steps in, the things in step 2, not that sentence what we have to do but the equations, then we will write this similar to what we wrote in the step 2 of example 3, that is cos minus pi by 4 is the x coordinate of P, which is this, and sine minus pi divided by 4 is y coordinate of P, which has the same magnitude but it's accompanied with a minus sign. Finally, calculations similar to those in examples 3 and 4 allow us to fill in the following table, in which we are going to show the values of the trigonometric functions, the first three, sine, cos and tangent, for some standard angles. Now, because we already know a similar table for the trigonometric functions in the acute angle case, so to make this table, to justify this table, we are going to include some negative angles also. Now the question is, do I have space for it? I have to somehow manage. Vertically I don't need much space, but horizontally I need space. This row will have the degree angles, this will have the corresponding radian angles, this one will have the sine values, and the one below it will have the cos values, and the bottom row will have the tan values. But we have many columns, 12 columns in fact. So it will be really tight, but I will try my best not to mess things up. here I don't even have space for writing. Here we have degrees, which I am just simply denoting by D. Okay, you have to understand. If you look in the text, you will see that you have degrees, and theta is in radians. So for that I am just simply writing R. And here you have sine theta values. Here you have cos theta values. Here you have tan theta values. In writing the values, however, we won't face that much of problem. Here, however, minus 180 degrees, minus 135. Oh, it's tighter than I expected. Minus 90. I hope you can make out. This is minus 135 degrees. This is minus 90. This is minus 180 degrees. Minus 45, 0, 30, 45, 60, 90, 135, 180. And the corresponding radian angles are minus pi, then minus 3 pi divided by 4. Minus pi divided by 2, minus pi divided by 4, this is 0, pi divided by 6, pi by 4, pi over 3, pi over 2, 3 pi over 4, and this is pi. 0, this one will be minus square root of 2 divided by 2. This one is minus 1. This one is minus square root of 2 divided by, these two are the same. And then 0, 1 over 2, square root of 2 over 2, root 3 by 2, this is 1, root 2 divided by 2 and 0, minus 1 minus root 2 divided by 2, then 0, root 2 divided by 2, this is 1, root 3 by 2, root 2 by 2, 1 over 2, cos 90 is 0, cos 135 is minus root 2 divided by 2, and this is minus 1. Now once you have sine and cos, tan can of course be calculated from these values. Just you divide the sine value by cos value. 0 divided by minus 1 is 0. These two values are same, so the quotient is 1. This cannot be defined because you have to divide by 0. So it remains empty. This cell is undefined. If you divide this one by this one, you get minus 1. 0 divided by 1 is 0. 1 over 2 divided by this is 1 over root 3, which however the author has decided to write like this. These two are the same, so 1. This divided by this is square root of 3, because 2 and 2 they cancel out. This cannot be defined because you have to divide 1 by 0, so this cell remains empty. This divided by this is minus 1, and finally this divided by this is 0. Okay, so this somewhat messy looking table because of lack of space shows some standard values of the trigonometric angles sine, cosine and tangent for some standard angle values. Now let me show you one thing. You may be wondering why the author is hellbound on writing 1 over root 2, which we generally write as this. One reason maybe is that some people don't like complicated quantities in denominator, but there is another reason, I think. You see, even if you forget these standard values, there is a very nice way to remember these values, and from these values you can actually find the other values. In fact, I will go so far as to include this one also. These values follow a fantastic pattern. No, I think, okay. Not exactly this one, but rather this one. Let me just see, okay, if I am remembering the thing correctly. This is 0, this is 1 over 2. If you just simply take square root in the numerator and denominator separately, you get square root of 2 in the numerator, in the denominator you get 2. Root 3 divided by 2, and this is 1. 0, 1, 2, 3, 4. So you can, if you remember this structure, then the numerators just keep on increasing one by one. But don't forget the angles, okay, 0, 30, 45, 60, 90. If you know sine theta, you can calculate cos theta, because sine squared theta plus cos squared theta is equal to 1. And if you know this acute angle sine theta cos theta values, the way we have calculated the other values, you can know the other negative and obtuse angle values. And once you know sine theta and cos theta fully, you know the other trigonometric function values. So with this, I am ending this video. After this, we have the graphs of this function. Looking at the graphs, you will see that these functions, particularly sine theta and cos theta, exhibit something known as periodicity. We mentioned this in the beginning of this section itself, that in regular intervals of time, I should not say time, in regular intervals on the x-axis, the values repeat. For example, you see this value repeating here for sine theta. So the graph of sine theta is like a wave, and this fact that the values repeat after regular intervals makes this function very useful in describing periodic phenomena, which is all around us. Seasons are periodic, simple harmonic motion is periodic, and many other things are periodic. Things happen again and again after regular intervals. Atomic vibrations are also periodic. Okay, so we will see these things as we go further and further into calculus. So that's just it for tonight. If you want to say something about these things, you can write in the comment section below, or you can of course mail me at my usual address. The link will be there in the description. So this coming Friday, today is Tuesday, so we have now gone through calculus. So coming Friday, let us do number theory, and then we will go to graph theory. And this coming Saturday, we again have Lee's algebra exercises. One of you was asking, so again let me remind you that Lie algebra exercises and Galilean algebra exercises alternate, and they come on Saturdays. So with this I sign off. So see you on Friday with number theory. Until then, this is me, Lucifer, from a mathematical room. Have a nice night.